For those of you who don't know me, my name is Michael Pope. I'm a professor in the Department of Chemical Engineering. And it's my pleasure today to introduce to you Professor Subhasis Ghosh from JNU University in India, in New Delhi. So Subhasis is here for two reasons, I think. So one is that we have a collaboration, and he was gracious enough to host me in New Delhi in April, and he showed me a great time. And I hope that reciprocating this visit to now. So, and also his son was accepted last year into our computer engineering department. So he's also visiting his son in the undergraduate program. So Subhasis Ghosh is a professor of physics in the School of Physical Sciences at Jawaharlal Nehru University. I have a difficult time saying that. He graduated from the University of Calcutta and received a PhD from the Indian Institute of Sciences, Bangalore. He spent a couple of years at the Max Planck Institute, Stuttgart, as a research associate. He's published more than 100 papers in reputed research journals. He is also a visiting faculty in the School of Electrical and Computer Engineering at Purdue University. His research interests are transport and optical properties of condensed and nanophase phases of organic and inorganic semiconductors. He has made significant contributions in optical and transport properties of wide bandgap semiconductors, physics and technology of organic field effect transistors, single organic molecule-based nanostructures, and the physics and technology of graphene and graphene-based field effect transistors. His recent interests are more so in materials for energy storage and phase transition and screw ionic host magnetic materials. So today I think he's going to talk to you about his work on graphene, in particular charge transport and doped graphene. So please join me in welcoming Professor Ghosh.
Thank you, Mike, for the kind introduction. And this is my first visit to Waterloo, and I'm enjoying my stay, both academically and socially. And having very nice discussion with some faculty here, Mike also, and to give a good shape of our project on energy, which I believe is the future. Energy storage, not energy generation. I make it a point. Energy generation no longer is an important area. Energy storage, and we hope to see a good results sometime next year, and plan to continue this collaboration for a longer period of time. Okay, today I'm going to talk about this this graphene work, which I'm doing for some time, but though recently it's a little bit of off color for different reasons, not for the academic reason. But before I go to the subject, I'm from New Delhi. It's the capital of India. We have got a fantastic campus. It's a 1,500 acre campus. It's a green patch in Delhi. Probably people say that's the lungs of the Delhi, because you can breathe a probably cleaner air only inside the campus, not outside the campus, because Delhi is air is quite heavily polluted. But that's why it's a quite a popular campus in Delhi. Okay. Now, before I start my this thing area, let me tell you how I earn my bread and butter. I have quite a still some activity on organic electronics, mostly organic field effect transistor, what we develop for back panel, this thing, TFT, support for the TFT, organic TFT. This is my new area. This is my magnetism and noble material, scabions. I don't know how many of you heard this term, scabions. Just let me explain you this. See that what is my feeling, and also I think that's a privilege, that there is not much problem in the processing. For example, all of you know that Apple, which just announced, or rather kind of came out with their iPhone, They have used 7 nanometer technology. Samsung has developed 5 nanometer technology. I think this will go till 3 nanometer. Okay, so I don't think there's not much of a problem. And silicon will be the material. Okay, silicon, I think years to come, silicon will remain the material. And I don't want to send a message that graphene is going to replace the silicon, because this is an absolutely wrong idea. People try to misjudge and misguide community by saying that silicon in steroid, graphene today, yesterday gallium arsenide is going to replace silicon. Those are not important. But the main problem with the memory, because for example, like this memory stick which I'm using here is a 16 GB, but we immediately need to put 16 terabyte of memory in that area. It's a small area. And presently there is no technology. NAND gate is saturating very fast, okay? So SSD will saturate within next couple of years. So we need a kind of a new carrier for the memory. And skyrmions is still in the domain of physics. I would say even the fundamental physics. It's a flower made of spins, okay? And its size, diameter can vary from a couple of nanometer to 100 nanometer. But it's a darling of condensed matter physics recently, because it shows an amazing phase transition phenomena, and whatever we learned in statistical mechanics you can apply there. Okay, it's a and lots of the new things, new physics supposed to come in skyrmions. This is just last couple of years people started looking into it. Fortunately, Mother Nature provided some of the materials where skyrmions can be observed. Like, you don't need to do too much of material engineering for doing that. But the point is that how you control. Best part of it, the skyrmions is topological soliton. These are mathematical words, but let me just explain you what is that. A topology means, you know, topologies, we talk about the kind of a shape, like all of you know donuts and the cup, and the cup, they have the same topology. But more importantly is a soliton. Soliton means, what is soliton? I think optical communication, you may have heard the word soliton, besides the mathematics. If an object moves in a system without any resistance, so that means there is no dissipation. So when the spins, when they are alone, they move, they find a kind of a obstruction, and that is the cause of dissipation. But this is a beauty of nature. When the spins make a flower, this whole flower can move without any dissipation. So essentially, yeah. So basically this is a dissipationless system. If any system is dissipationless, we know in mathematics and physics, possibility is infinity. There is an infinite possibility. Superconductivity is one of that like a example. So you can create, if you can create a memory, and I think people are having a strong hope on this. Third is the energy storage, which I am working on oxide nanowire-based supercapacitor and polymer and glass-based electrolyte. We'll have strong collaboration on this particular. And then finally, the graphene. And let me just discuss a little bit on where I kept. Oh, it's here. Sorry. Now, all of you know this is a wonder material discovered by these two gentlemen, Gaim and Novoselov, in 2004. But let me tell you, the graphene and its kind of a peculiar and spectacular properties were known long before, but it was all at theoretical level. These two gentlemen first showed that you can make the graphene so easily using the Scotch tape, and then subsequently they didn't get Nobel Prize just to make the graphene due to Scotch tape. People have a wrong notion. They first showed that the quantum Hall effect can be observed at room temperature in this system. And this system, I'm going to discuss, it has some connection with this skyrmions, that this system's electron behave relativistically. That means electron behave like a photons. And that's why this system is so spectacular, okay? And they showed this thing experimentally. So, and then immediately it was a very active area of research because quantum Hall effect, fraction quantum Hall effect, Kondo effect, Majorana fermions, these are typically, because I'm a student of physics, so it will be talk a little bit tilted, little bit in physics side, but if you want a clarification, you can stop me anytime and I'll be more than happy to explain this. So, but I'll try my best to explain if there is any technical term in the talk. So potential applications of graphene is a membrane for ultrafiltration, where Mike is expert on this, energy storage, sensors, and fast electronic devices. I have interest for quantum Hall effect, Kondo effect, and fast electronic devices. Today I'm going to talk about mostly on the electronic devices, okay? Now, what is graphene? Graphene is a one monolayer of graphite where carbon atoms arrange in the honeycomb lattice. Your building structure also is the best on the honeycomb lattice, and there is a reason I'll tell you. It will give you the after 3-4 slides you will realize that this gives a better stability also. That comes from the very fundamental physics, okay? So if you look at this lattice, it apparently looks like a very symmetric structure, but it's not. Why? Let us see. If you look at this carbon atom, which is presented by the black kind of a spot, it has one carbon atom top and 2 carbon atom bottom, right? But whereas the carbon atom which is represented with a white spot, it has 2 carbon atom up and 1 carbon atom down. What does it mean? It means that apparently it looks like a single lattice, but actually 2 sublattice is any honeycomb lattice is composed of 2 sublattice, 2 triangular lattice. And you won't believe all the spectacular properties of graphene tied to this fact that, so if you give me any lattice, 2-dimensional lattice, which is composed of 2 sublattice, you can predict the properties almost similar way, okay? So, though it is a hexagonal lattice, but it is actually composed of 2 triangular lattice. Now let us see what is the manifestation of that. Now, so this is one lattice and this is another lattice. So this is like a 2-level system. 2-level system in physics is represented by a kind of a 2-level kind of a, this is wave function. Let me make this point a little more clear. Now, in physics, whenever we came across 2-level system, rest is history, and kind of a excitement and revolution. Now, when we encountered the 2-level system last by 1927 by Paul Dirac, spin up and spin down when detected and experimentally verified. And this is again another example after so many years, this is another example where you observe the 2-level system because this lattice is composed of like a, so if you can say that this is like a spin up and this is like a spin down. Now this requires a little bit of kind of a history. Now, you know, all of us know that electron is a quantum particle and you should explain properties of electron or everything about electron by Schrödinger equation, right? Now, unfortunately, Schrödinger equation cannot give you all degrees of freedom. Now, let us see how many degrees of freedom for any particle electron. It has position x, y, z, 3, charge, and spin. So 5 degrees of freedom. In Schrödinger equation, we can manage 4 degrees of freedom, not spin. Then finally, 1921, Paul Dirac gave the first relativistic version of the Schrödinger equation, and again that was another milestone in our, I would say, civilization, because that has opened all the new physics, which is called relativistic quantum mechanics, quantum electrodynamics, particle physics, and all those things came subsequently from that equation. Now, let us do a reverse engineering. So spin and that Dirac equation can give you the spin naturally. Schrodinger equation, no spin, but Dirac equation gives you the fifth degree of freedom naturally, okay? So why that is the case? It's simple. Now what is the difference between Schrodinger equation and Dirac equation? If a particle moves very fast, we call it a relativistic particle, right? If a particle moves slowly, we call it a classical particle. Now relativistic particle, the particle which is moving a velocity close to the velocity of light, cannot be treated with Schrodinger equation because you will get a wrong answer. So you need a Dirac equation. So when a particle, that means fast, I get the byproduct as a spin. I get a two-level system. Now you do a reverse engineering. If there is a two-level system, that means the particle, corresponding particle, will have a very high velocity. And that is precisely the relativistic origin of why the velocity of the electron is so high in graphene. That's why you can get a almost a kind of a mobility in graphene which is unimaginable and never seen before. And if you make a transistor out of that, you can make a ultra-fast transistor. The whole idea is that. Okay. So now let us start with two-level system and let us see what is this effect of two-level system on the electronic properties of the graphene. Now before that, let me just spend a couple of minutes on the band structure. Okay, who are not the experts can excuse me, but the students, I'll just explain you this tight bending theory by 2 slides, and you can calculate the tight bending band structure of any material, I can promise you. How? Suppose I give you some lattice. What you should find out? You should find out the unit cell first. What is unit cell? Unit cell is the minimum space by which you cover the whole lattice. That means in this room, suppose if this is a 1 feet by 1 feet tiles, I can cover the whole floor. That means that is my unit cell. Okay? So I have to identify first the unit cell. And then once I find the unit cell, then I do the tight bending model, and then I get an energy dispersion relation, and that is the band structure. Now let us see how we will go from the unit cell. So what is the unit cell of graphene? Actually, hexagonal lattice, which is the real lattice, can be unit cell. How many atoms per unit cell? These atoms is shared by three kind of a honeycomb. So 6 into 1/3, that means 2 atoms. So either this is one unit cell. A unit cell need not be unique. It can be, there is a degeneracy. You can have a different kind of unit cell, but number of atoms of unit cell is a unique. So how many atoms per unit cell? 2 atoms per unit cell. Okay. So you identified the unit cell, and then you have identified how many atoms per unit cell. If there are 2 atoms, you have to solve Schrodinger equation to find out the band structure. You will have a 2 by 2 matrix. If you have 3 atoms, it will have 3 by 3 matrix. If you have 4 atoms, you will have a 4 by 4 matrix. There are 2 atoms per unit cell, so I have a 2 by 2. Don't worry about what is that. If anyone having an interest, I'll explain this term. So this is 2 by 2 matrix. You diagonalize the matrix, you get a band structure. Calculating band structure by tight binding method for any system is that easy. You identify number of atoms per unit cell, you will get a n by n matrix. If it is 2 here, 2 by 2 matrix, diagonalize the matrix, and then you will get a band structure, and this is the band structure. If I plot this thing, then this is the band structure of graphene. There's a very striking thing which never observed before in the history of physics or history of material science, that a 2-dimensional lattice can give such a kind of a odd band structure, I would call it, a very odd band structure. Now, but apparently it looks like, okay, we get to see this kind of band structure most of the material, but if you focus and if you look into a little detail, you have to have an artist eye. So you look into detail, and then you will see that this is a band structure which never observed before. Why? Let us see. Now, let us focus our attention on this. So I'm just zooming out this portion, and I get a band structure where E versus K is linear. Now, this is a problem because E versus K linear we get for the photons. Photon has a dispersion relation E, but graphene we have electrons or we have holes, they are not photons. So why should I get a band structure for electron which is like a same as photons? Now let us discuss. Let us now discuss what will be the kind of a projection on the electronic properties of graphene due to this very odd band structure. I'm playing with the electrons, but I'm getting the getting a properties of photons. Okay. Now let us see. Let us do it. Let us expand this. Just stellar expansion. And if I keep the first term and avoid the higher order terms, then 2 by 2 matrix becomes this. You don't need to worry about the technical thing. Just overall physics is enough. So 2 by 2 matrix. Now this diagonal elements become 0 and off diagonal element. So if I multiply this, then my Hamiltonian becomes sigma dot p. What is that sigma dot p? Sigma is the spin and p is the momentum. That's all. So that means sigma dot p commutes with Hamiltonian. Technically it's called. Colloquially, sigma dot p is a quantity which conserved in graphene, not any other term. Now what is sigma dot p? It's called chirality. Chirality word is popular in two fields. One is chemistry and another is particle physics. What is chirality? Chirality is nothing but is a projection of the spin along the motion of the electron. So spin is this up and electron is moving this way. So I have to take a projection of the spin along the motion of the electron. That is and that becomes conserved in graphene. And what are the kind of eigenvalue or what are the possible value of this chirality? +1 and -1. So what are the possibility? Either spin will be along the motion or opposite to the motion. So you can have two values, +1 and -1. So this actually makes the graphene completely different. So electron and holes are chiral. So it's not a normal electron and hole in graphene. It's a chiral electron and hole. Now, what will be the difference for normal system? Suppose all of us know that semiconductor has a conduction band and valence band, and we know that electrons and holes are in conduction band and valence bands are independent, and like we treat the electron and hole independently. There is no interconnection. But now the situation is completely different. In case of graphene. What is that? Now, in contrast, electron and hole states and graphene are interconnected. I'll spend a minute on that. What is the meaning of interconnection? And this kind of interconnection is observed in kind of a charge conjugation in symmetry in quantum electrodynamics, which is typically the foundation of particle physics and other areas. So that's all fine. Okay, I forgot to mention here. Now, this is the repetition. So what I'm trying to say, electron and holes are entangled in graphene. All of you know quantum computer. Quantum computer starts with this statement that if the electron and hole are entangled, then every state in the conduction band and valence band are interconnected. Okay? This is again a first time event. Never happened in any other systems, known systems we know, either biology, chemistry, physics, any field you think of. This has never happened before. So what we learned, now I think that's coming. So electrons in conduction band and holes in valence bands are entangled. Okay? So this entanglement makes all the difference. If I give you a piece of silicon, their electron and holes are independent, or any semiconductor, any material you think of. But here, this entanglement, and what is the manifestation of entanglement is the absence of backscattering. Now, I'm going to explain physically. Now, I have given you argument that why the velocity of the electron is so high in graphene, because they behave more like a photon, right? They are dispersion relation. But that's not enough, good enough for the solid state physics or chemistry, solid state chemistry. Now, let's see. Suppose an electron is moving this way, okay? Now, this electron motion will be disturbed if there is a scattering center, because scattering center is responsible for the finite resistivity of the system. Now, graphene is not like a material where there is no scattering center. They are full of scattering centers, because in a thermodynamics we learned that you can't create a system where you have a zero disorder. You have to have a disorder, right? Otherwise entropy will be, there will be a problem with the entropy. It will be a direct contradiction of second law of thermodynamics if you can make a system without any disorder. So disorder will be there. But it's what happens, and it's a very magical thing happens in graphene. Electron comes, and when you see disorder, if the electron is normal, it will see the disorder. But if electron comes, in many Hollywood movies you have seen this probably, when electron comes with a very high velocity, it will see the disorder no longer exists. Hollow manner kind of, there is a movie, exactly same thing happen in graphene. When the electron becomes relativistic, you see that nothing exists. You just tune down the electron velocity, you will see that the disorder appears. Because suppose an electron is moving this way, if it is little diverted from its path marginally, it's not a problem of the resistivity or mobility. If it is backscattered, suppose the electron is going this way, disorder or scattering center so strong that it backscattered. Then they actually decide the final velocity or final mobility of the system. But problem, this backscattering cannot happen in graphene because electron and holes are entangled. Now let me explain you the fact why. Suppose this electron, I'm representing this with the electron, and this is the spin. Now, if the electron is backscattered here, then it will behave like a normal electron. But it cannot, if it is backscattered, then electron will go from this state to this state. But this state is not an allowed state, because my spin this way, but if I have to go that side, then the spin has to be opposite. Unless there is a spin scattering center strong, this cannot happen. So this is no longer an accessible state for the electron. So backscattering is not possible. If the backscattering is not possible, in spite of the scattering center, electron will flow freely. And that is the actually bottom line for, or rather origin for such a high mobility or velocity of the electron. This is like a solid state explanation. The explanation I have given you before is more like a particle physics kind of explanation. Okay? So what is happening that this state, we know that in quantum mechanics, a particle can go from one state to another state provided three conditions satisfied, right? You have to have this state occupied, this state unoccupied, right? Then the electron can go from here to here. But if this state is occupied, Pauli exclusion principle doesn't allow us to go, and this is true for any area of physics. So now, if this electron can go up this side, provided I can flip the spin. But how else flipping the spin without any agent? Because there is no spin flipping agent is there. So that means this state is not accessible. If this state is not accessible, backscattering is not possible. So electron can zoom through the system. So that is the origin of the high mobility of electron in graphene. I have to explain this to you just to give you the kind of a flavor that why one can make one can fabricate such a ultra high speed transistor out of a graphene, and origin is this. Now, so what is the summary? What we have just discussed, that is a sublattice, two sublattices. This give a peculiar band structure, and this peculiar band structure gives rise to linear dispersion, where E is directly proportional to K. That is the manifestation of the relativistic carrier. And second is a chirality. Chirality means conservation of this quantity, that projection of the spin along the motion of the electron is conserved. These two facts make the super first transistor out of a graphene. Okay? Now that's all fine, that's all good, but let us talk about a little bit problem in graphene. Now, graphene is a zero band gap semiconductor. Okay? So that's why you'll have, if you make a device, you'll have a low on-off ratio. Till today, this problem cannot be solved. People are trying to use the bilayer, trilayer, and trying to do something, but I think there's a little bit of improvement here and there, but there is no kind of a total solution of this problem. Second is that it's extremely difficult to dope. And we know that the electronic revolution, if you ask me what are the facts responsible for electronic revolution, I would say two things. One is silicon. If you believe in God, that's a God-gifted material. And second is that ability to dope the silicon, to make it p-type and n-type. If I cannot make it p-type, n-type, silicon will be also useless. And that's what I just thought that so you can make a silicon p-type by doping silicon with a trivalent, or you can make it n-type by doping it pentavalent. So you have an extra electron and you have a hole here. And rest you know, p-n junctions, MOS, NMOS, PMOS, CMOS, this is possible just because of one fact, that you can dope silicon p-type, n-type efficiently. Unfortunately, this is a classical doping. This classical doping is not possible in the graphene, because as soon as you dope the graphene, you destroy the long-range ordering graphene, and all the spectacular of the properties of the graphene will be heavily compromised. Okay? Here I can give you the example. Suppose the mobility of the graphene is 10,000, it will be reduced to 1,000. That is the reason you don't get a high mobility in CVD grown graphene. Okay, now second is how to dope graphene. So if you want to make a transistor and invert a CMOS, then I need to dope a graphene. Now, as I said, that classical doping is not possible in case of graphene. So what you have to adopt something called quantum doping. So what is the quantum doping? Now before that, let me tell you how you grow graphene. We adopt all these three methods: mechanical exploration, chemical, and chemical vapor deposition. But I'm going to discuss about the chemical exploration, because that is a simple and you can get an excellent quality graphene by this method. Okay, what is that? Simple. You take a piece of graphite and then you put this graphite in a solvent. Could be any solvent, even the water. I'll show you some of the graphene we have grown with the water. Then you have to sonicate it with a certain time and then centrifuge it. After doing that, you will see that the monolayer of graphene just floating on the surface of the water or solvent. Take out the top surface of the solution, put it on any substrate, you have graphene. Not only you have graphene, you have an excellent quality graphene. And such a simple method, not even a $5 kind of a material you need for this, because you can use the low density graphite, which is extremely cheap material. Okay, so this is the graphene. This is the ACM image of graphene grown by this method. And how you are sure this is graphene? Look at this Raman signal. I'm going to explain a little more about the Raman signal. Let me tell you, this is a copybook kind of a Raman signal. Look at the width of the Raman peak. So that shows that is an extremely high quality graphene. You can prepare very simple method. Okay, and whole idea is that you take a HOPG or LDG, and when you sonicate it, you push the solvent molecule between the layers, and when you push this thing, they break the van der Waals bond, and that makes it graphene comes out of the graphite and floats on the surface. Okay, and these are the, now we have grown graphene, so you have to characterize it. This is the AFM kind of a, so you have to convince ourselves that we have got a monolayer, bilayer, and by this method you can grow only monolayer, only bilayer, only trilayer. So there is a selectivity, there is a strong selectivity in this method. So you see that here, when the green one, it's a monolayer, and red one is a bilayer. You can make out from the step 0.6 nanometer and 1.2 nanometer, okay? And second is TM. You see that this is a monolayer, these are bilayer. Monolayer, you can make out from the electron diffraction if you get a 6 spots, again back. There's a good problem in graphene. You know, I discuss about the kind of a, I discuss about what is that? Unit cell, okay? So hexagon is the unit cell in graphene. I just showed you, right? Now, in diffraction, what we see? Diffraction, we see the lattice in K space. A little differently, lattice in reciprocal space, okay? So how do you, so suppose this is the room, okay? It's a kind of a rectagonal shape. Now, how this room will look like in a K space, reciprocal space, is a little abstract, but you can check easily. What you do, you write a kind of, you take a Fourier transform of this whole geometry, and you will get a K space or reciprocal space. So diffraction is nothing but the looking at the object in Fourier space. Graphene, again, everything odd happens with graphene. The shape of the unit cell in real space and Fourier space, same for graphene. And that's why when you do the refraction, you exactly get the hexagonal lattice. It doesn't happen with any other two-dimensional material. Okay? So this gives you confidence, yes, this is another way of, probably the best way of checking whether you got a monolayer or not by transmission electron microscopy, okay? But just looking at the electron diffraction. Now, so I will show you, this is the graphene, it's a large area graphene, you can see 50 micron is the scale. We can get a large area graphene just by water. This is the sonication in water or DTO. D2 or H2O, whatever you can use. There's the advantage of using D2O that I can explain later. Okay, so excellent control, number of layers. This is trilayer, this is monolayer. How do you know monolayer? If this peak, this is called 2D peak, is more than double of the G peak, then we call it a monolayer. It has to be more than double. If it is little higher than 2D peak, then also monolayer. Bilayer is big opposite. If the G peak is higher than the 2D, and trilayer also, there is a way to know it. It's difficult to distinguish bilayer and trilayer. You need a look. You need a good eyes. You will see that is a width of the G peak in the width of the 2D peak in the trilayer will be a little more than the bilayer. That's the way, and that's little tricky. That's a little tricky, okay? But bilayer, monolayer and bilayer you can distinguish from, and Raman is the best way to distinguish whether you have a monolayer, bilayer. Trilayer is a little tricky. And again, you can see that from the width and from the width of the peak, you can see that the quality is excellent. Means, and this will be supported by the fact that when you make a transistor out of this graphene, and you will see that the mobility is really quite high. So how you are sure that this is the one fact which tells you that graphene is a relativistic and chiral. And a similar fact, for example, if I want to say that this particle is chiral, I need a accelerator which will be bigger than, which will be at least 10 times bigger than the Waterloo probably. So I have to generate that much energy by acceleration. But its graphene is nothing but a high energy accelerator just on a tabletop or not even inside a chip. And that this is the paper they have published, but the same group published in 2008, where they have shown that if you pass a light through the graphene, it is kind of a constant. 97.7% light only can pass through the graphene. And it does not depend on the material. But all of us know when you do absorption or transmission spectroscopy, absorption coefficient, everything depends on the material. But that chirality which I just discussed, if that conserved, then one can show, there is a theorem, one can show that the optical properties will be universal. It won't depend on anything. And you see that optical properties will be, like transmission coefficient will be decided by the alpha. What is alpha is a fine structure constant. This may be probably the student of physics can connect this alpha, which is 1/137, is decided by the velocity of light, Planck's constant. These two terms decide this. And you see there is no material parameter. And what about the bilayer, trilayer, multilayer? And you will see that bilayer, trilayer, multilayer, again this universality preserved. Because this bilayer, trilayer, there is no reason that the chirality should not be conserved. And instead just 1 minus pi alpha, you just can put 1 minus n pi alpha, where n is the integer. It's like a quantum Hall effect. So if n equal to 1, monolayer, n equal to 2, bilayer, n equal to 3, trilayer. So this simple absorption experiment also another best way to know how many layers is there in your graphene monolayer. Okay? Even I would say that this can compete, this method can compete the Raman and TM, probably better than TM even, because TM has some other problem in graphene. Okay. So, this is just what I said, that chirality conserved. Now we got a graphene, we have characterized, now we have to make a transistor. So I'll discuss what is this red spot. So we put a graphene on silicon oxide and make a source and drain, and then you have the transistor. And this is lithographically defined. If you want to keep the distance low, you can use the E-beam lithography. But I can tell you, even the shadow lithography is good enough for making a transistor out of graphene. You don't need E-beam lithography or photolithography. Any simple lithography is good enough. Okay. So this is a transistor, and so this is the Dirac cone. So what is the transistor? So you increase the gate voltage, your Fermi level goes up, and your Fermi level goes up. So your current actually decreases. Why current decreases? Because your Fermi level is going from high density of state to low density of state. And here density of state is 0. That's why current is 0. I can reverse the gate voltage, and then Fermi level goes up, again going from the low density of states to high density of state. And this is the Dirac cone, famous Dirac cone. And you can get to see that Dirac cone just using this transistor. If I want to see a Dirac cone for any other subatomic particles, as I said, I need an accelerator which will be 10 times more, the diameter will be 10 times more than the Waterloo and Kitchener area. You know, CERN is on 3 countries, right? Switzerland, Germany, and France. And you know that it's not good enough for the one country. That's why they have taken 3 countries. And the similar energy, just exactly, if I want to achieve this similar energy, I need that big accelerator for any other subatomic particle. But as I said, that the graphene is a kind of a accelerator on a chip. So this is let us see. So this is kind of a simulation. Let us see. This is called minimum conductivity point. This is a hole conduction. This is a electronic conduction, and this is called Dirac point. Now in the real state, this is so what we do, we put, as I said, that we put a 2 contact, source and drain, and then make a transistor. And see, this is like a low voltage region. You can get the Dirac cone. Now what is the mobility for this? Mobility is 10,000 to 30,000. It's quite good. It is such a simple way you can grow the graphene and you can make a transistor and you can get 30,000. 30,000 mobility means you can easily get 100 gigahertz transistor What is the gigahertz in your laptop? Is 2 gigahertz, 3 gigahertz? But such a simple way, if you make a transistor, you can get IBM's record is 300 gigahertz transistor out of graphene, and that too not a very good quality graphene. So easily you can make a ultra high, but again there is a problem that is a half of the story. On-off ratio for this is pathetic. So you cannot use this transistor for processing, but you can use this transistor for RF circuits, RF application, radio frequency application, or for communication chip. This graphene transistor will be the future, but not for the processing. Again, just word of caution: if anyone tells you that graphene will replace silicon, just don't believe. It's not possible. Silicon will remain as a silicon. But the whole point, take-home message is that such a simple way, just because of pure exploiting the quantum mechanical properties of the electron this has a deeper connection with topology again, that you can create such a high mobility, and this high mobility is the manifestation of the fact that chirality is conserved, and if the chirality is conserved, that backscattering is absent. Okay, fine. So now, fine, but this transistor is not a this transistor is a bipolar device. I have to make it N-type and P-type. Now, there are various routes of doping. These are I have just summarized it. But unfortunately, in all these methods, you disturb the graphene. As soon as you disturb the graphene, you compromise heavily the properties of the graphene. So you should adopt a method and make sure that conservation of chirality is not violated. And that is not violated provided you can adopt some quantum doping kind of a strategy. Okay? So what is the strategy? Now it will be a little bit of chemistry. You know that what is the strategy? Strategy is a simple idea. So you have a graphene. So you bring a molecule close to the graphene, okay, and choose the molecule so that one set of molecule will have excess of pi bond, another set of molecule will have deficiency of pi bond. So when you bring a molecule close to the graphene, make sure you don't make any bond, but excess of the molecule with excess of pi bond can donate electron cloud to the graphene. So without making it, you can make graphene N-type. Now when you bring a molecule which has a deficiency of pi bond, when you bring that molecule close to the graphene, it will take away the electron cloud from the graphene and make it P-type, and that's the strategy. But there is a technological bottleneck. Now, if I say that I can bring the molecule close to the graphene and I don't want to make a bond, then the molecule will go away. So what you have to do, you have to trap the molecule between graphene and the substrate. And you know, nothing can pass the graphene. Graphene is impermeable. Not even the helium gas even can pass through the graphene. So if you trap the molecule will remain there. Depending on their electronic properties, either it will take away the electron cloud or it will donate the electron cloud and making it P-type and N-type. Let us see whether that kind of a strategy works for the graphene. So again, now I'll explain. These are that trapped molecule. And it's very easy to trap molecule on graphene. So what you do, you put the solvent solution and put the graphene. And when you evaporate the solvent, the molecule which are below the graphene, they cannot come out, they get trapped. And then your graphene actually sticks on the surface of the substrate, trapping quite a few molecules. Now there is a way to change or rather vary the number of the molecules you want to get it trapped between substrate surface and the graphene. Now these are the two sets of molecules. There is a molecules with a excess of pi bond, and there is a chemist call it a electrophilic molecules and nucleophilic molecules. This I'm learning chemistry, so I'm not very comfortable with that. All I understand that one molecule has extra pi bond, another molecule has a lack of pi bond. Okay. So before doing the device, we do a detailed DFT calculation. DFT means density functional theory calculation. It's a first principle calculation, and we check that we try to simulate that, yes, if I bring that molecule, whether the charge transfer will be there or not. So once we see that DFT giving us some kind of a guidance, yes, choose this molecule, take it to the graphene, and then you will see the transfer, then we start the experiment. So before starting the experiment, we do DFT calculation for each and every molecule on the graphene, okay? And that's the kind of a little technical thing. If you have some question, I can answer it offline, okay? So now, let us first toluene. If I take a toluene and trap toluene between molecule between graphene and the silicon oxide surface. First thing that I have to convince myself, yes, I have trapped, and that's the best way of doing it, the IR. IR tells me, yes, because IR is the fingerprint of the molecule, yes, you got toluene trapped between the graphene and the substrate. Then I make a transistor. It's undoped because your Dirac point is close to 0. It's undoped. So that means toluene cannot dope. Toluene can get you only the pristine graphene, not the either p-type or n-type. And then what you did, this is the DFT result, and you see that this molecule is quite far. This result, this kind of a geometry, we get it from our DFT calculation. It shows that this toluene molecule actually at the edge and quite far. I'll give you the idea of the distance, how far, and how far is acceptable and how far is not acceptable. That means molecule, where should be the molecule so that you can see the effective doping, okay? If the molecule is beyond that distance, then the doping is not efficient, okay? So that means now, and it is expected because toluene dipole moment is very low, 2.3 or something like that. Toluene is a nonpolar solvent, and that's why toluene cannot either cannot give the electron cloud to the graphene, neither it can take away the electron cloud of the graphene. So you need a polar solvent, and that, let us take DMF. DMF is highly polar solvent. It's probably 37 is the dielectric constant, and you see that, okay, I forgot to tell you this. Let us see that is, you see that this G peak, this is a monolayer. This is called Confocal Raman. Confocal Raman, actually what it does, it scans whole area of the graphene and tells you locally what is the Raman intensity at each and every point, and then you create an image, and that's called Confocal Raman imaging. Now this is for the 2D peak is there, then G peak is there, but there is supposed to be the D peak, which comes due to the disorder in graphene, is absolutely absent. It's a flat. So that means D peak is not there in case of toluene. Now let us see what will happen in the DMF. Now DMF is there, and now if I make a transistor, this is the transistor characteristics. You see that the Dirac point shifted from 0 to minus 20 volt, is heavily doped. So I could transfer the charge from the graphene to the molecule and molecule to the graphene, okay? And now simultaneously you see that D peak is coming up. D peak is coming up. There is another, this is the DFT result. DFT result shows that the toluene DMF molecule is close to the edge of the graphene. And you see that this is the experimental proof. Can you see that from imaging, it's the yellow spots at the edge? That this confocal imaging actually supports our DFT calculation, because by confocal imaging, you can decide or you can get an idea who is responsible for your D peak. And now it is clear this peak is coming due to this attachment of the molecule. And in case of, let me give you the number, in case of toluene it was a 4 angstrom, and in case of DMF it is 2 angstrom. Okay, I'll come back to this point later. Now let us take another molecule, PC. PC is a 64 even higher dipole moment, and you see it's a even more doped. It was before DMF, it was 0 to minus 20, now it's a minus 30. And you see in this case, the PC molecule, it's a beautiful chemistry and physics. It's not understood well, where some molecule actually go the edge and why some molecules at the center. Now this molecule, PC molecule, is not at the edge. It's somewhere on the surface of the graphene. And that's again clear from your DMF, your confocal Raman image. You see that the yellow spot is scattered over the whole graphene. That means this molecule is there on the whole graphene. Okay, and simultaneously you get this peak also. So this is the summary of the DFT result, and this is the summary of the result. So these molecules, so I can make it p-type and n-type. If it goes to the left-hand side, it is n-type, and this is right-hand side, it goes to p-type. So not only I can make p-channel transistor, n-channel transistor, even I can fabricate the inverter, CMOS, which you eventually you have to fabricate the CMOS. So I can fabricate the CMOS by by doping it with a different kind of molecule. Okay. So now, how you are sure that what is the experimental proof that you are actually trapping the molecule? You have quite a good proof, but the best proof comes from the Raman. You see that as you increase the dipole moment, or as you increase the size of the molecule, this G peak shift gradually. And like you can calculate the stress, you can calculate, strain from this shift. Why there will be strain? Because if there is a molecule here, then the graphene will be bent, right? If the molecule is there, graphene will be bent. From this bending, you can calculate the strain, right? If you pull a string by like in a guitar, you can calculate what is the strain on your string by just calculating how much displacement is there in your vertical direction. Exactly same back of the envelope calculation you can apply, and you can calculate from the Raman shift what is the strain. And this is the strain. You see for the low dipole moment molecule, strain is less, but as soon as you increase the dipole moment, there is an order of magnitude jump in the strain. And this you can calculate the either from the Raman spectra or the method I just told you, by which generally we do it in a school to calculate the strain on when you pluck a string from any musical instruments. Okay, and this is the typically gives you the distance. You see that when distance between graphene and the molecule is very high, ID versus IG. ID versus IG, let me go back. ID versus IG means this is IG and this is ID. For this case, it is very low, and this case it is very high. And that's again, you see that when the distance is 4 angstrom, that ID versus IG is 0.01, but when the distance is close to 2.5 angstrom, it is close to 1. That means you are convinced that this ID is responsible, is due to the organic molecule you are putting on the graphene. Not only that, this distance actually what you are supported by your DFT calculation is actually responsible for how much electron cloud will be donated or will be taken away from the graphene. Okay, how much time I have? I should wrap up. Okay, fine. So I'll just quickly, I'll take 2 minutes, just give you some idea that fine, you got a graphene, you got a transistor, but you should know this thing, fabrication is not enough, or speed of the transistor is not enough. You should have a clear idea that who is responsible for giving you the finite mobility. You can ask me the question, if the velocity, if the electron in graphene has the same property of the photon, it should have an infinite mobility. Why it is stuck to 30,000? If it is a freestanding graphene, it is 10 to the power 6 centimeters in square per volt. But why 10 to the power 6? Why not 10 to the power 12? And here I can show you, I think I'll just summarize here, that remote interface phonon act as a dominant scatter at room temperature, and the lattice defects in graphene and substrate impurities play dominant role at low temperature. What is the remote interface phonon? Because when you put the graphene on substrate, then the phonon in the substrate will disturb the graphene, and at room temperature they decide the finite mobility of the graphene. And this is unavoidable, because if you want to make a device graphene, you have to put graphene on some substrate. Till today there is no solution to this problem, how you can reduce the scattering of the electron by remote interface phonons. So that is, I'm just giving you this flavor. So what are the problems we have still? There is a scope of future work, and what are the problems to be solved? This is one of the major problems. But in spite of that, you are getting a mobility which is 1,000 times more than the best silicon or gallium arsenide transistor in the market today. So that's quite amazing. And I think I'll stop here. Thank you for your attention.
Thank you very much. Does anybody have any questions?
So why are graphene transistors terrible at processing?
It's not terrible in processing. You can make even, I know that already RF chips are made out of graphene. Main problem with the graphene transistor is the low on-off ratio.
The low what?
On-off ratio.
Okay.
Low on-off ratio is the main problem for graphene transistor. But if you want to use it for simple switching, it is fantastic. It's better than any other material, existing material. But if you can create a finite gap in the graphene using, now there is a one method what we are trying. You put a lot of molecule both side and create a lot of corrugation in the graphene. If you can create a lot of corrugation in the graphene, and that can open the band gap, because your on-off ratio depends on the band gap. Simple calculation says that right now the on-off ratio is pathetic, 10 to 20. Now to take it to 100, you have to create a band gap of 0.3 electron volt minimum, where silicon has a band gap of 1.2 electron volt, gallium arsenide 1.4 electron volt. These are quite comfortable band gap to have a high on-off ratio.
Next talk. I have two questions. First question is, you mentioned that the substrate will influence the mobility.
Yeah.
So your mobility is 30,000 something.
Yes.
So what's the substrate used for the science paper? They got like
This is silicon oxide.
Silicon. This one no this problem as you.
Some interface engineering can be done and being done. For example, there's a group in Maryland, they are trying to do it on strontium titanate. I don't think that there's like a dramatic improvement in the mobility as a marginal. Special treatment, some group reported that if you do the nitration before putting the graphene on silicon oxide, you get a better mobility. But this is like I don't think there is any first principle guidance what to do and what not to do. It is both. It is at the level of trial and error. Do something, you can get, but still we don't know how to manage the remote interface phonon. Because if you can reduce the effect of remote interface phonon by 50%, you can increase the mobility from 30,000 to 80,000 easily.
My second question is, so you mentioned the traditional doping will induce some
Defect, yeah.
Reduce mobility. Like your method, it's better like only like a bondable or kappa interaction. So how's the mobility of your transistor up to?
This transistor, the transistor which I just shown you, their maximum mobility we got at 30,000. On an average, you get a 20,000.
So I mean, compare the one without doping.
Oh, compared to, yes. No, I got. Compared to like a covalent doping or any other doping, I think its maximum mobility till today is 8,000 only.
So can I have one more?
Yeah.
So you have a simulation using EMF molecule. So that one only interact with the edge of the graphene. Right? But if it's the case, if you use graphene, it's pretty large. I think it's pretty large in
Yeah.
cases. So EMF only interact become effective. Then in the center, probably won't that effective, right?
Yeah, right.
I don't know. So in this case,
Yes.
if you
And
have
I got
some string just cover the only mirror center, where the DMF model won't be that effective.
yeah.
But
I know.
why you got
Yeah, I got your point. So you mean to say that doping will be at the edge, not at the center. It will be a non-uniform doping. But in transistor, that will be a problem for example, kind of a device where you have to use a local probe. But transistor, current will go from source to drain by the easier path. So the point is that when you apply the gate bias, so graphene is almost gives the equipotential surface. So suppose it will behave like a remote doping, though the doped it here, but that carrier can go anywhere. So that there won't be a problem of creating the depletion channel and kind of pinch off.
Maybe let me follow. Doesn't your Raman results though contradict that?
Pardon?
The Raman results, like I think the DMF one also shows that there's strain-induced DP. Correct?
Yeah,
So
yeah.
doesn't that sort of say that there's probably also DMF between the substrate and the sheets? Because otherwise you wouldn't have strain if it was just constant.
Yes, yes. No, let me just go back to this and see, if you look at the PC, the strain for the PC is much higher, maximum. And our this result, and DMF is less than PC, because these are the two high dipole moment molecule we have used. Now look at here, in case of PC, you see that the molecules is distributed, and that's why you got the maximum strain. But in case of DMF, it's at the edge, but edge is maximum, but you see that there is a reason to believe why I got a less strain in case
so
of
the
DMF.
Raman that you're showing in that other figure is only like showing the edges, I guess, like for this.
No, that's what I'm saying. See, if you look, this is the confocal image for the D band. Now here you see the yellow spots a little more on the edges, right? These are because this is the actually size of the graphene. But the point is that all we can do, we can compare with PC. PC is equally distributed. So strain in PC is always more than the DMF. That's all. So we can make a comparative study that way.
Question over here? Oh, Irene.
So you say that mobility is reduced because the dopants interrupt the long-range order.
Yeah.
And in silicon, when we dope, it also interrupts the long-range order. So can you explain why it's more
Yeah,
important?
yeah. This requires a little long explanation. See, graphene is a purely quantum material, okay? So the resistance, what we understand classically, is replaced with the quantum resistance in case of graphene. Ohm's law is replaced with the Landauer's law. What is that? Is there any pen on paper? Something? Okay, anyhow, let me tell you. So what happened that resistance in quantum resistance is determined by the transmission coefficient of the electron from one side to another side through a barrier. What is barrier? Barrier represents your scatterer. Okay. Now that barrier, the height, transmission coefficient depends on the height of the barrier. If the barrier height is high, then the transmission coefficient is less. So what happened that in case of when you make a covalent bonding, then this barrier is very high. But when you make a kind of a remote bonding, this barrier is very low. So low that your transmission coefficient is only the 10% less than very high barrier. So that is the reason that long range ordering is not disturbed by such a low barrier. So here our traditional concept of classical resistance, what we learned from Ohm's law or what we learned from the Maxwell-Boltzmann theory, it becomes kind of unapplicable. It comes with only the height of the barrier and transmission coefficient. And for this kind of bending, so making it short, this kind of bonding the barrier height is much less than the covalent or ionic bonding barrier. Yeah.
One last question.
Yeah, I was just wondering if the transfer current, like when it's put for the transistor, would it like, are we checking out the spin properties of the current?
No, we have not done. We have
Because
not.
One thing that I think it might be relevant is that, like, say I have some chiral structure, like which we can make with some biomolecules, like some chiral structure. So there is evidence that the spin of the electron transport in this medium is spin dependent.
Yeah. Yeah. No, I got to your point. Now let me explain you why the spin measurement is not relevant. The reason is simple. Suppose the electron is coming with a spin up, okay? Now the question is that when it reaches the other end of your conductor, the spins will be totally random, because up spin remains up spin in a distance which is called spin relaxation length. The similar like a mean free path in normal scattering. Now what is the spin relaxation length for spin in graphene? It's only 2-3 nanometer, and our source drain distance is 10 micron, 1 micron to 10 micron. That is too high compared to the spin relaxation length. Whereas is a 3 order of magnitude higher. So that's why it will be impossible to detect any spin polarization. If I want to see a spin effect of spin polarization, I have to fabricate a graphene transistor with a gate length of 1 nanometer or 2 nanometer. That is not we cannot fabricate. And then we need a spin polarized source and drain. Spins polarized source and drain, that means instead of gold or copper, you have to use iron, cobalt, nickel, because you have to inject the spin polarized electron, right? And that can be injected only from the ferromagnetic material, not from the diamagnetic material like copper and gold. And then making a transistor with a 1-2 nanometer channel length with a iron and cobalt, I love to do it, but it's a kind of difficult job.
So if anybody has any other questions, you can stay. Professor Ghosh is going to be around, I think, for another half an hour or an hour. So.
And tomorrow I'll be here in the morning also.
Tomorrow he'll also be here, so if you're interested in meeting him, please send me an email. Otherwise, let's thank Professor Ghosh for a great talk.